Hi, so I'm going to go through the evens on this just to get you used to this process. Okay, so in number 2, actually, let me quickly talk through number 1. So an object is dropped and falls a distance h in a time t. So instead of giving us numbers for these quantities, we're just given letters instead, but we treat them exactly the same way we would numbers. The first thing we're asked to do is derive an expression for t, the time, in terms of h and fundamental constants. So besides the letter t, the only thing that can show up in my answer are operations, like, times and divide and square root, or numbers. And g is a number. We're actually not going to replace g with 10 or anything like that, because if we leave it in terms of g, then this expression will work on Mars or the moon. So we just leave g in the answer. Okay, so since this is free fall, our acceleration is negative g. Since it says that it's dropped, our initial velocity is 0. I started with the displacement equation arranged for the y direction, and so you can plug in the letters whenever you want. I decided to do all my algebra before I replaced the quantities with the givens. So you'll see that I isolated lowercase t in terms of the variables in the original equation, and then in this step, replaced the variables with the values given in the problem. And so my final answer has only h, the number 2, and the number g in it, and so this box has completed the task. Okay, so for number 2, an object is dropped from rest. The initial velocity is 0. And you don't even really need the meters per second, honestly. I'm going to not even bother with that. The initial velocity is 0, and it dropped from rest, and it falls a distance h. Now this is capital H, so I'm going to just make sure I'm careful about using the upper or lower case as indicated in the problem. Reaches a speed v max just before hitting the ground. Okay. Now that is downward, so it is negative, but it said speed, so I'll just leave it. Well, it is negative. Derive an expression for v max in terms of, okay, so the acceleration in free fall is negative g. Okay, so we do not have time, and we're not looking for time, so we're going to use the equation that doesn't have time in it. So that's vf squared equals vi squared plus 2a times delta y. So vi is 0, and we're trying to isolate v max. Oh, so we're pretty much already there. So now I'm just going to take the square root of both sides. Okay, and so now, before I am done, all I have to do is go through and replace every quantity with its equivalent from my givens. So Vf is Vmax. And since Vmax is a speed, I am just going to worry about the positive side of it. Then this is square root 2. The acceleration is negative g. The y displacement is negative h. And the negatives cancel. There we go. So checking back that I only have what I'm allowed in terms of h and fundamental constants. All right, we're good. Okay, so this negative's bothering me. Boop. Okay, so when we're trying to determine whether a quantity on the other side of the equal sign would increase or decrease our desired unknown, it simply just is it on the top of the fraction or the bottom of the fraction. So in the first one, you see that the first relationship I established was between the time and the height fallen. Oops, I thought that was going to be a highlighter. Height fallen. And so we see that the height is on the top of the fraction, and so time is proportional to the square root of h. So remember, this little guy here means is proportional to. Okay, so time is proportional to the square root of the height. Increasing the height would increase t. G is in the denominator. So if g goes up, t goes down, and in this case, though, it's asking about decreasing, so if g goes down, t would go up. Okay, so on B, what effect would decreasing the height have on Vmax? Well, Vmax is proportional to square root h. So whatever happens to h, the same relationship would happen to Vmax as far as like increasing, decreasing. So if h gets smaller, Vmax would get smaller as well. What effect would increasing the gravitational constant have on Vmax? Well, Vmax is also proportional to square root g, so increasing g would increase Vmax. Okay, number 4. A ball is thrown vertically at a speed v sub r and returns to its original height in a time t. Okay, so v sub r is my initial velocity, and it returns to its original height in a time t. Okay, so it returns to its original height, so delta y is 0. And the v final, or v2, did I use I or f? Okay, we'll use I and f. Would be negative VR. It comes back to where it started, and so whatever speed it lost on the way up, it's going to gain on the way back down. It's still free fall, so the acceleration is still negative g, and we are looking for the time. Oh, but it's called capital T, sorry. Okay, but that's our unknown. Okay, so I actually know kind of a bunch of stuff. Since I'm looking for t, though, I am going to go with this one. It seems simplest. So Vf is neg Vr. Vi is Vr. Oh, nope, sorry. I was getting ahead of myself. We're looking for t, so let's go ahead and isolate that first. Vf minus Vi over A equals t. Okay, now I'm going to go ahead and replace my variables with the quantities that were given. So Vf was negative Vr minus Vr over negative g equals t. T equals negative 2Vr over g. And so those negatives cancel out. T equals 2Vr over g. Okay, let's double check that I didn't mess anything up. We're looking for t. We're allowed to use Vr and fundamental constants, so that 2 is a constant and g is a constant. Great. What effect would increasing the initial speed have on the time in the air? Time is proportional to Vr. Increasing Vr would increase t. And hopefully that makes sense, right? The faster we throw it, the longer it's going to spend in the air. What effect would decreasing the gravitational constant have on the time in the air? Okay, well, t is, not equal to. T is proportional to 1 over g. Decreasing g would increase t. So if I went to the moon, which has this weaker gravitational field, and threw a ball upward with the same speed, it would spend more time in the air because of the weaker gravitational field. All right, number 6. A car that is moving with a speed v1 stops with a uniform backward acceleration of magnitude rho and needs a time t to come to a stop. Oh, this is the same equation as last time. Oops. Maybe I'll do a different one. That's boring. Yeah, I'll do 5 instead. Okay, a car that is moving with a speed vc stops with uniform backward acceleration of magnitude a and needs a distance d to come to a stop. Derive an expression for d in terms of vc and a. Okay, so we don't have time. We're not looking for time. We are looking for d. So first I just isolated what I'm looking for, and actually I could have actually gotten rid of this earlier. Vf is 0. So now I'm going to go ahead and plug in what I have. So that's Vc to negative a, and delta x is called d. So d equals Vc squared over 2a. All right, what effect would decreasing the initial speed have on the distance traveled? D is proportional to Vc squared. If Vc goes down, d would go down. What effect would increasing the backward acceleration? Okay, d is proportional to 1 over a. If a goes up, d goes down. Okay, hopefully you're kind of getting the hang of it. Ooh, these get a little weirdsies. Okay, so I'll do 7. A car that is moving with speed 2v increases its speed to 6v while moving in a straight line with an acceleration a. This change takes the time 2t. All right. It's a little strange to say t equals 2t, but it's just saying that the time is equal to 2 times t. This t is some number. Okay, so we want to derive an expression for a in terms of v and t. So starting to start with vf equals vi plus at again. So vf minus vi over t. Ooh, that is an ugly fraction bar. Equals a. Now I'm going to go ahead and plug in what I have. So 6v minus 2v over 2t equals a. 6 minus 2 is 4. So we're just going to, technically you could box it there. That's true. And we are allowed to use v and t in our answer, but it's just kind of, good form to clean something up like this. So 6 minus 2 is 4. Then 4 over 2 is 2. Okay, so we can do normal algebra with these. Like we can combine them in any normal way. What effect would increase in the value of v? Okay, a is proportional to v. Increasing v would increase a. And what effect would increasing the value of t have on the acceleration? A is proportional to 1 over t. Increasing t would decrease a. So hopefully you're kind of getting the hang of it. It's just something that just takes practice, and just like treating letters like numbers definitely is a little unfamiliar. If you have any questions, keep track of them and we'll go over it together.